Okay, it's Wednesday. We're here starting Unit 3. Okay, I'm lying. It's not really Wednesday, it's Friday night, but I'm a couple days late on getting this lecture up. We're starting the third unit, Chapter 27, which is we start to deal with current and resistance. So we spent the last few chapters dealing with potential, which is voltage, and electric field. And if you go to the analogy with water circuits here, which I will for sort of going out of order here, um, remember that we have some source of potential like a battery which separates charge, and that charge leads to an electric field, and that's analogous to a pump in a closed water loop. And now we're getting into this chapter, we're going to get into the flow of current through the wire, which is produced by this electric field, and that's analogous to the flow of water in a closed water loop. So you can think of voltage like pressure pushing electrons, and you can just like you can think of a pump which pushes water through the system. And now we're going to talk about the flow of electrons, which is current, and that the same role is played by the flow of water in a closed water loop. So we're going to discuss current and resistance to current in this chapter. I think you'll find this easier than chapter 26 conceptually. This chapter's not too bad. So I'm going to post homework 9 on Monday, maybe probably, and I might make the due date another day later. But this homework assignment should be short, and it should be way easier than the assignments you're doing. We're starting Unit 3 in this chapter. Remember, Unit 2 exam is Monday during the synchronous lecture on chapters 22, 23, 25, 26. So let's get into this. So by definition, what current is current is the flow of charge through a conductor. Conductors, remember, are metals. And if you have a circuit, that current moves through wires, and the wires are connected from the source of energy, which is a battery or power supply. The batteries connect the energy source to the circuit that's using the energy, your device, your cell phone. And so they're connected by conductors. And so current is the flow of the charge, the electrons, through the conductors. So why do the wires have to be conductors? Okay. Well, if you look here, each metal as a whole is electrically neutral. But remember, electrons are free to move in metals. Okay, so each atom on average typically donates about 1 electron to the metal, where it's not the most loosely bound electron is free to move around in the metal and is not bound to that atom. And so since it's neutral, each electron that moves around leaves behind a positively charged ion that's fixed. And so you have these electrons, and they tend to move around, but if you don't apply an electric field, they move around, they smash into ions, they move around, they smash into another one, they go back and forth, sort of like a drunk in a bar, and they tend not to really have any net migration along a particular direction. Okay, they're just randomly smashing into ions and moving around. So if you have no electric field applied to the metal, these electrons are just moving around randomly, smacking into ions, but there's no net motion. So we really need an electric field applied to the wire. In other words, we need a potential difference between the two ends of the wire. And then what happens here is superimposed on this random motion, this drunk-like motion where they're smashing into ions, superimposed on that is a net migration of the electrons against the field. Remember, the positive charges move along the field, electrons move against the field. And so once you apply an electric field, you get a net displacement of the electrons against the field. And so we define the current as the charge per time passing a given point in a conductor. Okay, and I'm going to call it a wire because wires are conductors, and that's the most typical example. So here you've got a wire, and at time t, what the current is it's a measure of how many coulombs of charge pass a given point in a second. Okay, and if you don't have an electric field, and these electrons are smashing back and forth, but there's no net motion along a given direction, then the current is zero because there's no net charge per time going through this region in a particular direction. So in other words, without a potential difference or an electric field, there's no current. Okay. So we define current as the charge per time. Charge has units of coulombs, time has units of seconds, and we call this unit of coulombs per second an ampere, and we give that this symbol A. Now most of us know this as amps, so when you say there's 10 amps of current in a circuit, it's 10 amperes, or in other words, 10 coulombs per second on average past a given point. So we can call it amps, amperes, has the symbol A, and it's the current per charge per time flowing past a given point. So what factors would you guess would influence the current? So here we've got a wire, and the wire has a cross-section area A, and we're measuring how many amps or how much charge per time cross this given point. So you might guess that the charge per time depends on this average drift speed of the electrons. In other words, what's the average speed at which these electrons are migrating, in this case, from left to right? Okay, so if they're moving faster, then you're going to get more current, right? You're going to get more charge per time crossing this point if they're moving faster to the right. In other words, if the electric field is larger and they're moving from left to right faster. So then you would guess it would depend on this drift velocity. Okay. Another thing it would depend on is how many electrons are in the wire, right? So in other words, how many electrons per volume are in the wire. And since each atom in the metal typically donates on average 1 electron, this is basically the number of atoms per meter in the metal, which is the atomic density. So the more electrons that are free to move, you're going to get more charge going past a given point. The faster they're moving, the faster they're drifting, you would guess that they get more. And the third, which isn't so obvious, but yet it is, if this cross-sectional area A is bigger, in other words, if the diameter of the wire is bigger, you're going to get more charge passing a given point, right, than if you have a smaller diameter wire. And so if you put all of these together, you get that the current is equal to the charge per electron, which is just E, times the electrons per second, that gives charge per time, and the electrons per second depends on the density of free electrons in the metal, which is a property of the metal, depends on the area of the metal, and it depends on how fast these electrons are moving, this drift speed. And we'll see later that the drift speed depends on two things here. If you go back here, so you go to our analogy here of the drunk in the bar smashing into people and yet migrating toward the door at the end of the night. So you're going to get a larger drift speed if you're not colliding as often, right? And so the time between collisions will make the drift speed faster because you're not spending as much time smashing into ions. And also, as we increase this electric field, then this drift speed is also going to increase. And so it depends on the drift speed, on the electric field, and it also depends on the time that the electron takes in between collisions. If it collides less, it's going to go end up with a greater speed to the right. So the current then depends on these three factors. So the three ways of increasing the current in a wire are by, first of all, you can increase the drift speed, either a larger field or less collisions. You can increase the wire diameter. Okay, that's why wires with larger diameters can handle more current. Okay, for example, if you have an extension cord with a larger diameter, that can be rated for a higher current. And the third is you can increase the number of conduction electrons, and that's fixed by the metal that you choose. And so in these metals, you see that like copper and silver and gold and aluminum, they've got a huge number density of electrons. So about, for example, copper has 8.5 times 10 to the 28th electrons per meter, or 8.5 times 10 to the 22 per cubic centimeter. So there's huge numbers of electrons that are free to move in these metals, and that's usually the guiding factor in how good of a conductor of electricity they are. And that's why metals are good for or for pushing current through a circuit. Poor word choice. So let's do an exercise here. So suppose you have 4 wires, and the first one has a cross-sectional area R, and you have a drift speed V. Second wire, we keep the same diameter, the same radius, but the wire is moving twice as fast, the electrons. In other words, maybe we apply a bigger field, or we have less collisions. The third, we make a larger diameter wire, and then the fourth, we have this larger drift speed, but a smaller radius. And so what we want to do is we want to compare the current in each case. And so you might guess that the largest diameter wire wins, but let's see. So we plug this in. The current, remember, is the charge of an electron times the number of electrons per volume times this cross-sectional area, which is pi r squared, times the drift speed. Okay. Now in part B, everything is the same, but the drift speed is twice as big, so we put 2V in instead of V, and what that gives is you get twice as large of a current. So in other words, twice as large of a drift speed along the material, along the metal, twice the current. The third one, we have twice the radius. And since the area is pi r squared, that means we have 4 times the area if we have twice the radius. And that gives us 4 times the current that there was in wire A. And then the fourth one, we have twice the speed, so they're moving faster, but we only have half the radius, so the area is 1/4 pi r squared. And that ends up being only half the current of A. And so the answer in this case is that wire C has the largest current, followed by B, followed by A, and then D is last. So the most influential variable, it seems to be, is the diameter of the wire influences the current the most. It's because it's proportional. Current is proportional to the square of the radius or the square of the diameter. So if we want more current, we increase the diameter of the wire. That's one way of doing it. So another useful quantity that's used when we talk about current and the flow of electricity through a wire is what's called the current density. And that's obtained by taking the current through the wire and dividing it by this cross-sectional area A. And that's the amps per meter square. So that's what's called the current density. And what happens there, if we take our expression for the current, and we divide this by area, it's equal to the charge of the electron times the number of electrons, the conducting electrons per volume, times Vd, which is the drift speed. And so this is a property of the metal, and the drift speed is a property of the metal and the electric field. So we've canceled out the effect of larger diameter. So current density is another way of describing the flow of electrons through a wire. So what we've done is we've calculated the magnitude. Now, the direction of the current. Okay, well, we know that the current is due to electrons moving through the wire. Okay, so technically, in this case, it would be the electrons. If you have the field pointing right to left, the electrons would go against the field. And so really what's going on here is the electrons are moving left to right. Okay, however, before they knew about which charges were moving, Ben Franklin guessed wrong and guessed that it was the positive charge that was moving. And probably because he was Ben Franklin, nobody wanted to tell him, or they just didn't know then. But they've always kept this sign convention. So the current is typically described in terms of positive charge and in moving along the direction of the field, even though it's really the electrons going in the opposite direction. So even though we know that the electrons are moving toward more positive potential, the current is defined by definition to be the direction in which positive charges are moving. And we know positive charges move from higher potential to lower potential. And so when we start talking about current in circuit, we'll talk about the quote positive charge moving from higher potential to lower, even though we know what's really happening physically is it's the electron moving from lower to higher. Okay, mathematically both pictures are equivalent. So we're going to treat this in terms of positive charge moving from higher to lower potential. So that's our definition. That's our direction of the current. So now that we have that, next thing we're going to get into is what's called Kirchhoff's current law, or conservation of charge. And this forms one of the building blocks that we're going to use to analyze circuits in the next chapter. So let's suppose that you have a battery or you have a capacitor, and we hook up these two light bulbs in series. Remember, series just means we daisy chain them one after the other. So here's the positive terminal of the battery, or it could be a charged capacitor. We hook one end of the wire up, we hook the other one to the battery, then after the battery it gets connected to the second battery, and then back to the light bulbs, the second light bulb, and that gets connected to the negative terminal. And there's one loop, right? There's only one path for the current to flow, and it's through the first light bulb, through the wire, through the second light bulb, back to the battery. Charge gets pushed over to the other terminal, and there's only one loop, and we say that's what's called wired in series. Okay. Now Kirchhoff's current, what happens is a consequence of conservation of charge. Okay. And since charge cannot be created or destroyed, it can't pile up or disappear anywhere along these wires. It has to just keep moving. In other words, what comes into the light bulb must come out at the same rate, because charge can't just pile up here. And so then one of the consequences is that the current is the same everywhere in this series circuit. Okay, and it's tempting to think, okay, if I asked you which bulb will glow the brightest, okay, and I do this when we have in-person class, Most people will say the first bulb. So you say, okay, well, why? And they'll say, well, the charge gets used up and going through the first bulb, and there's not as much available for the second bulb. Okay, now that isn't true because the current can't pile up. In other words, the charge doesn't get used up. The current's the same through both bulbs. And so, somewhat counterintuitively, both bulbs will glow equally bright. In other words, the current is the same everywhere in this series circuit. The charge can't just pile up at any point. Another consequence of this happens when you have a branch in a circuit. Okay, so you can think of this as, if you think of this water flow, you can have a pipe, and this can be a T-connector right here. And so the water flow would come through, and part of it would branch off and go through each of these pipes at the T, right? So that's the same with current. So here comes the current, and the current encounters two possible paths, right? One part of it can go up, part of it can go down. Now, Kirchhoff's current law says that since the charge can't disappear or pile up here, whatever rate that the charge comes in, charge per time or current, whatever it comes in must be the rate at which it comes out. So let's suppose that we have 10 amps of current. It's pretty big current for most circuits. Suppose 10 amps is coming into this junction. Well, then a total of 10 must be leaving. So maybe 5 go to the top, 5 go to the bottom, or 6 go to the top and 4 go to the bottom. But in other words, whatever current comes into this junction must also come out. The sum of the currents leaving must be the same as the sum of the currents entering the junction. And that's called Kirchhoff's current law. Your author calls it something else, but most of the world calls it Kirchhoff's current law. We'll call it KCL, okay, not to be confused with the chicken franchise. So Kirchhoff's current law says that the sum of the currents coming in equals the sum of the currents coming out. And this is going to form one of our building blocks of circuit analysis in the next chapter. So let's do an example here. Question is, what is the magnitude in the direction of the current in this fifth wire here? Okay, so here we're going to use Kirchhoff's current law, which says that the sum of the currents entering this junction must be the sum that's leaving. So let's look at everything that's accounted for. You've got 3 amps coming into the junction, and then you have another 4 amps coming in from this wire. So you have a total of 7 amps coming in from these two currents. Okay, now we look at these 2 wires here, and you have 6 amps leaving plus another 2 amps leaving. So you have 8 amps leaving and 7 amps entering. Okay, well, Kirchhoff's current law, KCL, says that the sum of all the currents entering must be equal to the sum leaving. So that means we need 1 more amp of current coming in or entering this junction toward the junction to even it out. So then we would have 1 amp coming in plus another 4 plus another 3. That means 8 amps coming into the junction equals 8 amps leaving, and they balance, okay? So this answer here is that you must have, this current must be 1 amp, and it must be going toward the junction, entering. So Kirchhoff's current law is really easy. It just says the total coming in must equal total coming out. And that's a lot like water flow. If you have a T connector, whatever comes in must come out. The water can't disappear at the T. All right. So the final topic that we'll get into today. See, I told you this chapter is easier than the last one. So we go back to this drift speed. And remember, we go to our model of the drunk in the bar. So here we go back. Right here, remember, if you have an electric field and you have these electrons and they're smacking into the positive ions that are stationary, then they go smack into another, And if you apply a net electric field, like a voltage across the wire, then in addition to smacking into these ions, they also tend to have a net drift, in this case from left to right. And so the drift, your author derives this in the chapter. This drift velocity depends on the rate at which these electrons are smashing into the ions, right? If they're spending more time smashing into ions, they're going to tend to migrate more slowly toward the right. In other words, the drunk takes longer to get to the door if he's smashing into more people as he goes there. So this drift velocity depends on the time between collisions. Let's go back here. And we're not going to derive this, but your author does, and we're going to use it. It depends on the electric field, right? In other words, we apply a stronger electric field, the electrons are going to drift more rapidly against the field. And then it depends on these constants, the charge of the electron and the mass. So the drift speed depends on the time between collisions, which they call tau, and it depends on the electric field E. So, and E is the field strength pushing the electrons through the wire. So if we plug this into the current density, remember current density is current per area, and we derive this, it's the charge of the electron times the density of electrons times the drift speed. We plug all of this in for the drift speed, and we see that the current density depends on the electric field. In other words, what's this pressure, if you think of it in terms of pressure, pushing the electrons along the wire. And then it depends on a bunch of other stuff. I got to get rid of the equal sign, that's a typo here. A bunch of other stuff in this parenthesis, and these are just a bunch of constants which depend on the metal, right? The mean free time between collisions, the mass of the electron, the number of electrons per volume. All of this stuff is a constant which depends on the metal, and we call all of this stuff in the parenthesis the conductivity of the material. And we denote that conductivity with the symbol sigma. This is what is a Greek letter sigma, and that's called the conductivity. Conductivity has really weird units. It has units of 1 over ohms. We haven't even defined ohms yet. Ohms is the resistance, and times meters. So don't worry about the units yet. It's got some funky units here. But the conductivity is a measure of how good of a conductor the metal is. In other words, how easy is it for electrons to flow through this metal. And so if we call all of this stuff in the bracket the conductivity, then the current density J is equal to sigma times E. And that's a more common form. So in other words, if I want more current density, I apply a stronger electric field, right, to push the electrons through, and I pick a metal that it's easier to get the electrons to flow through, and that's called the conductivity. So this is yet another expression which relates the current, or in this case the current per area, to the conductivity of the metal and the electric field strength pushing the electrons through the metal. So the main point here is that the current in the wire then depends only on the electric field strength and on the properties of the metal, how good of a conductor it is. One thing that we haven't discussed is that the conductivity, in addition to the properties of the metal, depends on temperature. So in other words, at higher temperature, the electrons are going to have more energy, they're going to be moving around faster, and they're going to be smacking into the ions more often, and that will lead to lower conductivity, right? In other words, there's more thermal agitation. they're smashing into the ions and moving around more, but really not moving along the direction of the field. So at higher temperatures, the electron conductivity is lower. It tends to conduct less current. Now, it's more practical in electronics to speak of what's called the resistivity, which is just the inverse of the conductivity. So we can flip the conductivity, right? It's the electrons per volume times the square of the charge of the electron times the time between collisions divided by the mass. If you take the inverse of that, we get this property called the resistivity. And while the conductivity is a measure of how good the metal is at letting electrons flow through it, in other words, how much charge per time can flow through it, the resistivity, like its name implies, is a measure of how much the metal resists the flow of current. And that has units of ohms per meter. And you see here that the big variable influencing the resistivity is the time between collisions, right? If there's more time between collisions, there's less resistance to flow. If there's less times between collisions, meaning smaller tau, there's more opposition to flow. So it depends on the time between collisions, and it also depends inversely on how many electrons are free to move around per volume. If you have a greater electron density of conducting electrons, that's going to be less resistance to current. If you don't have as many electrons free to move around, that's going to be a bigger resistance to current. And so if we write it in terms of that, we can write the current density either in terms of the conductivity times E or in terms of 1 over the conductivity, which is the resistivity, times E. And here's an example of some metals, okay? Copper has a real high conductivity, as does silver and nichrome, and so they tend to have a low resistance to flow. So in other words, it's easy to push electrons through copper wires. There's not as much resistance to flow. It's easy to push electrons through silver wires because there's not as much resistance to flow. Carbon wires wouldn't be a very wise choice, right? They have a lower conductivity or greater resistance to flow, and so a given electric field strength would not be able to push as much charge per time through a carbon wire. Okay, that's why you don't see carbon wires. But you do see carbon resistors. These are devices, these are little components whose sole purpose is to limit how much current goes through a wire, and we'll talk about why later. And so some of these resistors are made out of carbon. They're also made out of tungsten. That's a tungsten lamp. Incandescent bulbs, we'll get into that later. So in other words, materials with higher conductivities like silver and copper have a greater flow of electrons through for a given electric field than materials like carbon or tungsten or nichrome. So let's end with an example here, and there's a purpose for this. We'll see in a little bit. So suppose you have a silver wire, and we can look up the conductivity of silver. So silver has a conductivity of 6.2 times 10 to the 7. And suppose that the diameter of the wire is a 0.5 millimeter. And suppose that the wire carries 20 milliamps of current. And a milliamp is 10 to the negative 3 amps. So what we want to do first is we want to calculate what's the electric field strength in the wire, and then second we'll calculate what's the electron drift speed, VD, in the wire. Okay, so we go back to our formula here. What are we given? Well, we know I is 20 milliamps. We know the diameter of the wire, so we know pi r squared, that's the area. Okay. we can calculate we know the conductivity of the metal because we can look it up for silver. So we can calculate the current density and we know the conductivity, and so we can get the electric field strength, and that's what we're going to do. So the electric field strength is the current per area, which is J divided by the conductivity. We plug in current, 20 milliamps, or 0.02 amps. We plug in the area, cross-sectional area, pi r squared, and then we looked up the conductivity for silver, and we get that the electric field strength is 1.64 times 10 to the negative 3 volts per meter. So that's the electric field strength. Okay. Now we know the current per area, and we know we can look up the number of electrons per volume in silver. We'll go back here, so here it is back in this table. Where is it? Right here. The electron density in silver, there's 5.8 times 10 to the 28th free conducting electrons per meter cubed. So we know Ne. And now we can go back to here. Okay, we plug in the charge of the electron, and we plug in the number density. And we know the current, we know the area, and we get the drift speed of the electrons is 1.1 times 10 to the negative 5 meters per second. Now, in addition to plugging in numbers and showing that we can calculate this, the purpose of this example is twofold here. The first is that the drift speed of electrons in a metal is really small. Okay, so this, look here, 1.1 times 10 to the negative 5 meters per second. That's like 11 micrometers per second is the average speed of the electrons as they migrate along the wire. And so if you go back to our drunk in the bar model here, that means that these electrons are spending most of their time smacking into the ions, and they're having a very slow drift along this opposite the field. But this VD, the drift speed is very, very small. So then you think, oh, well, if they're moving so slow, how do we get a large current? Okay, well, we do because there's so many electrons that are able to move. So in other words, the electron density of silver is 5.8 times 10 to the 28th conduction electrons per meter. So even if they're moving very, very slowly past this given point, if you have that high of a density of electrons, you're still going to get a fairly high charge per time moving past this point. Even though each electron is moving slow, you have so much charge migrating left to right that you're going to get a high current charge per time. So it's not that they're moving fast, it's just that the number density of these electrons is so high in the metal that any little electric field to get them to drift is going to result in an appreciable current. So that's the first point of this example. And then the second point is that this electric field that's pushing the electrons through is pretty small. We calculated much bigger values in the last few chapters. And that, again, is it doesn't take a real large electric field to get a fairly high current, just because we have so many electrons that are slowly migrating from left to right that even a small field that will get them to drift can give an appreciable current. So those were the main points here, is that this drift speed really is pretty small and the electric field is small, but this number density of electrons is so high in metals that you can get a pretty high current even without a fast speed of the electrons or a large field. So that pretty much ends this first half of the chapter. we're going to finish chapter 27 tomorrow, which is Thursday. This is a pretty short chapter. It's pretty easy. And then we move on to, we're going to use this and the last chapter as our building blocks for circuits in the next chapter. So we will catch you tomorrow. Have a good one.